Hello, welcome to the course Electronic System Design. Last few lectures we are discussing about some combinational logic and sequential logics where we can develop certain gates, NAND, NOR gates, inverters and all different types of gates to implement a logic function which is useful for us in developing the complete electronic system. So, most of the time in digital electronics we implement certain functions using these gates, and these functions are generally implemented using the help of Boolean algebra, which we discussed last time. There is a separate course on digital VLSI design which discuss more about this Boolean algebra application. So, that we are not going to discuss here, but Boolean algebra is extensively used for implementing these logic gates and optimizing the function to the minimum value possible, so that the hardware cost actually reduces. If we have a longer expression for a same function, we need more number of gates and more number of operations to implement that. However, if we can optimize the function using Boolean algebra, we can reduce the cost in terms of number of gates. So, we need less number of gates to implement the same logic function, and if we have lesser number of gates, then we need a small area on the silicon and the cost of fabrication also it reduces. So, that we discussed last time. Today we are going to discuss about the logic families. What we have something called logic families, which represent kind of technology or the digital circuit is used to implement certain functions. So, the same function, same Boolean function we can implement using multiple types of technologies. For example, there is a MOSFET or CMOS based technology. We have transistor logic where we use BJTs to implement the function. We can use sometimes diodes itself to implement a logic function, for example, NAND NOR gate. So, we have certain types of logical families available by which we can implement the same logic function. So, today we are going to discuss the logic families, and then we will discuss certain data sheet of a product. When we buy something from the market, how the data sheet actually look like, what are different sections in the data sheet. So, that we are going to discuss today. So, logic families represent kind of digital circuits logic family represent kind of digital circuit or the methodologies for logic expressions. So, first let's discuss how can we classify these different technologies based on the number of gates we used on a single chip. So, let us call it as a scheme and the number of gates per chip. So, on a single piece of silicon, how many gates we have, based on that we can classify. So, the first one is the small scale integration, or SSI we call it. This is called SSI in short, and typically we have less than 12 gates on a single chip for SSI. Second, we have the medium scale integration. Or MSI in short, we have typically 12 to around 99 or 100 gates on a single chip. After this we have large scale integration. We call it LSI, and in this we have typically 1000 gates on a single chip. After this we have very large scale integration. Or VLSI we call it. In this we have around 10,000 gates on a single chip. After this we have ULSI or ultra large scale integration. In this we have typically 100,000 gates on a single piece of silicon. And after that we have giga scale integration or GSI we call it. In this we have 1 mega gates on a single chip of silicon. So we have, based on the number of gates we are integrating on a single chip, we can define the scheme as SSI, MSI, VLSI, ULSI and GSI. And till now we have discussed like logic gates. So in logic gates, typically NAND NOR gates, we have 3, 4 or 5 transistors. So that falls under the SSI logic scheme, where we have less than 12 gates, 12 transistor on a or the 12 gates on a single chip when we form a complete chip. Then we discuss the combinational logic gates or the sequential logic gates. Those combinational and sequential logic gate, they falls under the MSI or the medium scale integration. We have typically 12 to 100 gates on a single chip. And then we have something called microprocessors, which we use in our laptops and all electronic gadgets. All those microprocessors, they fall under the VLSI or LSI logic scheme, where we have large number of gates implemented on a single chip. So this is how we can differentiate between the logic family based on the number of gates. So, for example, the IC logic gates falls under SSI, combinational logic circuits, falls under MSI, and processors falls under LSI and VLSI. Then we have the digital logic family which we are discussing. So, these logic families can be classified broadly into number of technologies based on how they are built. So, let us discuss digital logic family. So, these logic families can be classified broadly according to the technologies they are built. So, there are various logic families. So, there are multiple logic families. The first one is the diode logic, or we call DL in short. Then we have resistor transistor logic, or RTL we call in short. Then we have diode transistor logic. This we can call DTL. Then we have emitter coupled logic. Or ECL. We have transistor logic. Or TTL. And then we have CMOS logic, which is very much used. So these are the various logic families we used for implementing the logic function. And typically TTL and CMOS logic family is most widely used in IC technologies. So the TTL and CMOS logic families are most widely used IC industry or IC technology. Each family has different rating for speed, power consumption, temperature range, voltage levels and current levels and so on. So each family has its own rating for speed, power consumption, temperature range, voltage levels and current levels. So as we can see, we have different types of technologies available to implement the same logic function. For example, diode logic, in which we use only the diodes to implement certain logic function. We have resistor transistor logic, where resistance and transistors are used. Diode transistor, where diode and transistors are used. Emitter coupled, where we take the output as the emitter. Transistor logic, where we used completely transistors, which are BJTs. So we use BJTs to implement a logic function, which is called TTL, and then we have CMOS where we have PMOS and NMOS to implement certain logic function, which is CMOS logic. And among these we recently use only TTL, the transistor logic, means the BJT we use for the logic implementation, or we use CMOS as a logic implementation. So, these are the two technologies which are widely used nowadays. Each family has its own rating for speed. So, for example, if we use BJT, the speed is different than CMOS. The power consumption, which is generally higher in BJT, because BJT is a current control device, the current is flowing all the time. So, that actually increases the power dissipation. However, MOSFET, we do not draw current at the gate. So, typically CMOS has lower power consumption. Temperature range is different for both of the technologies, as well as the voltage levels and current level, how much current it can provide. For example, the MOSFET, it does not draw any current at the gate. So, current levels at the gate is very less. However, BJT, it draws current at the base junction. So, the current level required to put the input at the base, it is different. So, based on the technology we use, we have different parameters for different technologies. Now, let us see quickly how a CMOS logic look like, which we are discussing from quite some time, and then the same circuit, how does it look like in any other technology. So, let us consider a simple CMOS logic gate, which is a NAND gate, which is a universal gate. So, a CMOS NAND gate look very similar to this. We have two PMOS on top and two NMOS in series at the bottom. So, this is our NAND gate using CMOS or the PMOS and NMOS transistors. The symbol for this, which we have already seen, is something like this. Now, if we implement the same logic function using some diodes and transistors, let us see how it look like. So, let us first draw the truth table for this NAND gate, so we understand well. We have here A, this is input B, and then we have output. So, for each combination of 0 0, 0 1, 1 0, 1 1, we have this 1 1 1, and this is 0. So, this is the truth table for NAND gate. Now, let us see how a NAND gate in TTL logic or the transistor logic or the diode transistor logic look like. So, this is how the gate look like. First is, let us say we have resistance here, Then we have diode connected here, which is input A. We have another diode, this is input B. At this node we have a resistance connected, this goes to a BJT. This is, let's say, R1, this is R2, and this is R3. So this is how a NAND gate in the DTL or TTL look like. If we look at the input A and B, they are applied here through this diode. Let's consider one case at a time. So let's say both the inputs A and B both are 0. That time, because this intermediate point, this, let's call it this X. So the node X is actually fed high through this VDD. So, and diode A, signal A and B are connected to ground, which is the first line A and B. That time the diode will be turning on because this side is high and this side is low. So the diode will be drawing power and pull this node X to ground, which is low. So when this node X becomes low, this BJT will turn off because emitter is grounded and the base is also grounded through these diodes. So this BJT will turn off, and when this BJT will turn off, the output will be pulled to VDD using R2. So the output will be pulled to high. So this is the first line where signal A and signal B both are 0, then output is high. If in fact any of the A and B is high, any of the A and B is low, A is 0 or B is 0, the same phenomena will happen. A and B signal will be 0, so diodes will turn on and this node X will be pulled down to 0. It means the BJT will turn off and output will be high. So in all these three lines, either A is 0 or B is 0, the output is high. So in the second line A is 0, it means the output will be high, and in the third line the B is 0, it means this will be also turned high. In the fourth line where we have A is 1 and B is 1, it means A is also VDD and B is also VDD. 1 is the logic level high, which is VDD. In that case, A and B both are high. This node X is also high because of the R1 is connected through VDD. These diodes will not turn on because A and B signal both are high. So this X node will be pulled up to VDD through this R1 resistance. When this node X is high VDD, that time the BJT here, its base to emitter voltage is higher than its threshold voltage. So base voltage is VDD and emitter voltage is 0. So this VB is very high, so this BJT will turn on. As soon as the BJT will turn on, this node out will be pulled down to 0 because there will be a current flowing from VDD to ground, and because the saturation on resistance of BJT is low, this collector to emitter resistance is low, so the output will be pulled down to ground or the very less value. So the output will be 0 as soon as the A and B both are high. So this is how this NAND gate works, which is made up using BJT and diodes and resistance. However, here few interesting points to note here is, when this output is pulled down to ground through this BJT, the output value is not exactly 0. However, this is 0, which is ground. The output value will never be completely 0, because the output is nothing but the resistance dividing of between R2 and the on resistance of this BJT. When this BJT is turned on, it is not like BJT has 0 resistance between the collector and emitter. It has certain resistance. Let's write it with a different color. We have a small resistance on resistance of this BJT. That time the output is simply the resistance divider, let's call it this R1, small r1. So output node voltage is the resistance divider of R1 and R2. So R1 divided by R1 plus capital R2 into VDD. So the low value of output node is not exactly 0, but it is a function of R1 and R2. Typically R1 is very less than R2, so it may be very close to 0, which we desire, but it is not, because R1 and R2 both are finite numbers and VDD is also typically 5 volt or so. So this 0 volt is not exactly 0, but up to a very close to 0, maybe few millivolts. So that time we can say the output high value is completely VDD. When this BJT is turned off, output will be pulled to VDD. So we can write the actual voltage levels here. So this will be, output will be VDD, here will be VDD, here will be VDD, and here for 0, this is not exactly 0, this is R1 divided by R1 plus capital R2 times VDD. So the 0 value actually depends on this ratio, and how do we design. So typically we want a very less value of R1 when BJT turns on. The on resistance of this BJT should be very, very low, and R2 should be very, very high. But it had its own drawbacks. So for example, we have R2 very high. In that case, if R2 is very, very high, that time it will take lot of time in pulling the output node to high, because it can provide now the less current from VDD to output. So the output, which is typically a load capacitor, this load capacitor will be slowly pulled up to VDD, because the R2 is very, very high. If we keep R2 very, very low, then the R1 should be much more lesser than this R2, which is again a problem. We typically have certain on resistance of BJTs or MOS transistors. We cannot decrease them beyond a certain level. So R1 has its own value. R2 we need to have very, very high compared to R1, but if we increase it beyond certain level, the pull up and pull down timings will be degraded. So we have trade off between the speed and the actual logic value of the output, which is the ground voltage R1 divided by R1 plus R2 into VDD. So, we have to decide at what point we want to have this R2 resistance fixed, because this is going to dictate our logic levels. Now, let us discuss what are these logic levels, because when we are discussing these logic gates, we are assuming that the voltage coming in from these logic gates is typically 0 volt for 0 logic and VDD for the logic level 1. So, this is our expectation, but based on the technologies, these levels are not meant. For example, here itself the output high is completely VDD, but output low is not 0, which is at a certain level. So, according to this, now we need to define what is a proper input and output levels of these logic gates. So, input at the input logic, for example, we have a gate at the input, we need to specify what is a acceptable logic 0 and what is a acceptable logic 1. Similarly, for the output also we need to specify what is a accepted logic 0 and what is a accepted logic high. So, based on this, we have now 4 definitions to specify logic 0 at the input, logic 1 at the input, logic 0 at output, logic 1 at the output. So, we have 4 definitions to decide. So, let us discuss these definitions. Input output voltages for TTL family, and same is applicable for CMOS as well. So, for example, we have 2 gates, one gate is driving the another one. This is supply VDD and this is ground. This gate is driving another gate which has again the supply voltage VDD and ground. This is 0 volt. So, now let us say this is our complete VDD level from ground. Let us say this is our complete window from 0 volt to VDD for this gate at the output, and then this is the complete voltage window for the another gate. This is also from 0 volt to VDD. So, now we are talking that this gate is driving the another gate. Let us say this is A, this is B. So, gate A is driving gate B. It means the output of gate A, this is output of gate A, should be compatible with the input of gate B. So, this is the input window of gate B. Now, we are saying that due to the technology used, whatever technology we are using, these 0 volt, exact 0 volt is not possible. The logic low will be low value, but not necessarily it can be a 0 volt. It can be up to a certain point. Let us say this is the level this is the level where input can be based on small r1 and r2 ratio. Output low need not to be at 0 volt, but it can be within a range. This is my logic 0. I still accept this value as logic 0 up to this point in voltage. So, y axis is the voltage and up to, let us say, 200 millivolt, let us say this value is 200 millivolt. So, I accept this as a logic 0. Again, for the high value, it necessarily need not to be VDD. Currently, we just see in the last slide VDD was perfect, but because of in the other technology, it may be possible that VDD is not perfect. That is also a ratio of some resistors. So, this VDD need not to be a complete, this logic high need not to be complete VDD, but can be a lower value less than VDD. Let us say typically 200 millivolt lesser than VDD. So, this is still acceptable as logic 1. So, if my output of this gate A is between 0 volt and 200 millivolt, I still accept this as a logic 0. It means the logic 0 has come, and if my output of this logic gate A is 5 volt or 200 millivolt less than that 5 volt, I still accept that as a logic 1. That logic 1 has come and it should be detected by the next gate. In between this range, this is abnormal operation, or I would say I will not decide if the voltage level is in between this value. So, this I can call, let us say, abnormal operation. Now, this logic 1 and this logic 0 need to be perfectly detected by the gate B. Gate B has its own voltage range from 0 to VDD. So, the detection range or the threshold values of this input, this B gate, should be somewhere here, so that it is satisfactorily detected by the next gate. So, this is my logic 1 and this is my logic 0. Here we can have one question, that why not we put these values equal. For example, this is the point where I detect output as high. This should be the same as at the input of logic B. The answer is, many a times these logic gates are not perfect. For example, this value, let us call it, let us say 4.8 volt. If we define 4.8 itself for the input also, but because of the mismatch when we fabricate these gates, because of the mismatch, this 4.8 is not exactly 4.8. We need to have certain margin so that it is perfectly detected by the input. So, we need to have certain margin or certain overlap, so that this, because of the mismatch, if this 4.8 becomes 4.89 or 4.9 or 4.75 or something, still that value is detected by the input of gate B. So, we need to have little bit mismatch or the overlap between input and output. So, based on these definition in these logic levels, now we can write the definition of VOH, VOL and VIH, VIL, which are the logic levels for these logic gates. So based on this, we define VOH VOL and then VIH and VIL. So VOH is the minimum output voltage in high state. VOL is the maximum output voltage in low state. Similarly, VIH is the minimum input voltage can be detected logic 1, and VIL is the maximum input voltage that guaranteed logic 0. So these are the 4 definitions of VIH, VIL and VOH, VOL, and we saw that this need to be having a mismatch. These VOH and VIH value cannot be kept at the same point because there will be a mismatch while during our designing and after fabrication. We cannot align them for all the chips and ICs. There will be a difference. So we already keep a margin so that when we join these two circuits together, there is always a margin we have, and which the output high is satisfactorily detected by the second gate. So these are the definitions, and now let's see how a complete IC actually look like when we have these logic gates inside the ICs. So let's see some IC packages. So this is just some image taken from the internet. These are the IC packages. These are made by their respective manufacturer. So this is dual inline package where we have a IC, and both the sides we have these pins coming out which connect this IC to the board. If we see the diagram of this IC, for example, we have these 7 pins. So we have these 7 pins, and this is a notch to align. This notch is actually this notch. Inside this we have, let's say, these NAND gates. This NAND 1, it has 2 inputs, one at the pin 1 and pin 2, and pin 3 is the output. So in this IC, for example, we have, this is pin 1, this is pin 2, and this pin 3 is the output. So when we apply the logic expression A and B at 1 and 2, then output is taken as at the third pin. So this is dip package or dual inline package, which is very widely used in fabricating these logic gates for integrated circuits. So, here we have a single IC where we have implemented 4 NAND gates 1, 2, 3 and 4, and typically 1 to 9 logic gates are generally available in a single chip. So, we can characterize based on the number of gates we have. So, when we want to have, let us say, one particular logic gate, NAND gate, we go to market, we go to these manufacturers, buy their ICs. That comes in this ceramic package where we have dual inline package typically for these logic gates. These pins behave like a logic gates when we have, let us say, pin 1 is input 1, pin 2 is input 2 and pin 3 is the output of this logic gates. So, we need to just bias them properly using this ground pin and VCC pin, which is here and here. So, we use this IC to use the NAND gate or NOR gate, whatever we need in our logic circuit. When we buy these logic gates, we buy these ceramic ICs from the market, and generally a document sheet or the data sheet is provided along with this. We call it PDS sometimes, product development kit, PDK or PDS, whatever manufacturer call them. So, this is a data sheet which specify how this IC is going to behave. Let us see that data sheet, have a look at that data sheet, how does it look like. So, this is a typical data sheet which you can download from internet. So, in this data sheet you have various sections. For example, here it is shown that it is a dual inline package where we have 4 NAND gates connected from 1, 2 as the input and third pin is the output. If we go down, we have various sections. Let us go quickly on this section. The first one is the specification where it is mentioning the minimum and maximum the ratings. So, for example, the first line, which is VCC, it is specifying the supply voltage, and the maximum value of this supply voltage you can put is 7 volt. When you connect this IC to any circuit, it should not exceed the supply voltage of 7 volt. Then input clamp current, that is maximum 20 milliamp you can put. The output clamp current maximum 20 milliamp, again continuous output current is 25 milliamp you can draw. Continuous current through VCC or ground, it is acceptable as 50 milliamp. Junction temperatures, depending upon the package you are using plastic package or hermetite package or die. The maximum temperature is 150 degrees centigrade. You should not increase this temperature. Storage temperature is also specified between -65 and 150 degree. Then there is a ESD rating. For example, when you touch a electronic circuit, there can be electric discharge. Your body can accumulate certain charge and that can be discharged. So, there are two models. One is human body model, for which there is a 500 volt of tolerance, and for CDM, which is charged device model, which is 750 volt, this device can sustain. Next we go to recommended operating conditions. In normal operating condition, your supply voltage should be 5.5 volt, not the 7 volt. 7 volt is the maximum voltage you can apply, otherwise beyond 7 volt the device will be damaged. So, normally you should have a minimum of 4.5 volt and maximum of 5.5 volt as a supply voltage. High level input voltage should be 2 volt and the low level input voltage should be 0.8 volt. So, this is actually VIH and VIL level. So, VIL is from 0 to 4.8. So, 0 to 0.8, that logic level will be detected as low, and VIH level is 2, minimum 2 volt. Input voltage is 0 volt and maximum is VCC, and the output voltage is also between 0 and VCC. Input transition time is 500 nanosecond or 400 nanosecond depending upon the supply voltage, and operating free air temperature is minus 55 to 125 degree centigrade. So, these are some of the values which are specifically given. For example, here it is given in detail VOH, VOL, VOL, IC and delta IC. So, these are some of the parameters which are used in data sheets, which are given for the accurately connecting these IC to the different ICs, so that these VIH, VILs are compatible to the other logic. So, when you buy 2 or more devices, 2 or more types of devices, and you want to join them together, you need to make sure that VIH, VIL levels are matching with VOH, VOL level in the same way what we decide in the second last slide. The VOH, VOL levels should have certain overlap between VIH, VIL levels. This is how we connect the circuits together and they work reliably. So, we need to carefully look in the data sheet for those circuits what we use. So, this is all for today. Thank you.